So today I'm going to be talking to you about composing classes with TypeScript. So to begin, let me introduce myself. My name is James, and I'm a software developer who works with a variety of languages and technologies, but primarily JavaScript and C#. I've gained experience at a variety of companies such as Sky, Channel 4, Trainline, and Net-a-Porter. And I contribute back to the community via open source software, mentoring, articles, and speaking commitments. And I work for a consultancy called YLD. And we're a software engineering firm specializing in JavaScript, particularly Node, React, and we started doing some DevOps stuff, so that's in terms of helping the companies establish that culture, but also some of the technological aspects like cloud and containerization as well. We have offices in Manchester, Lisbon, Porto and London, and some of our most prominent clients include Thomas Cook, The Economist and Trainline. Also, I omitted it from this slide, so we're hiring, so if you're interested, then come and grab me after the talk. So enough of that anyway, let's get stuck in with the technical nitty-gritty. So, first of all, what is TypeScript? Well, it's a JavaScript superset based upon ECMAScript, so like JavaScript is now, it's fully compliant with that specification, but it provides us with additional typing capabilities. It's statically typed. So the variable and parameter types are known at compile time, and as a consequence, TypeScript has a compiler that performs this static analysis before transforming TypeScript code into JavaScript code. So it allows us to catch errors earlier. Generally speaking, it's able to infer type information very well, so we don't always have to explicitly annotate our code. However, there are instances where we can provide these type annotations, and in some cases, we must provide said annotations. Built-in type definitions are available for JavaScript globals, the DOM API, and also for built-in browser objects as well. But there's a really useful project called Definitely Typed that provides additional definitions for a variety of libraries and JavaScript technologies, the most prominent being Node. And it's developed and maintained by Microsoft. So if anyone here uses C#, then you may be familiar with Anders Heilsberg, the lead architect of that language. He was also the pioneer of TypeScript, but the development is also driven by the community and a variety of open source contributors. And it's open source and licensed under Apache 2.0, so you can reuse it and distribute it without any legal qualms. So let's have a look at an example. So we have a one-liner here, and you may be thinking, well, this just looks like standard ECMAScript, like, where's the typing? Well, this is what I was saying about its inference capabilities. More often than not, you don't always have to provide these explicit types. So what this example will do is it will get the UTF-16 code unit for the first character in that string A and assign it to a constant called first code unit. Now, if we try to compile this as we are below with the TypeScript compiler, which is invoked via the TSC command, then we'll see that it fails because an argument of type 0 as a string literal is not assignable to a parameter of type number. So in using this, it allows us to catch these trivial errors earlier that could catch us out in a specific browser in production. So let's have a look at a bit more of an involved example. So if we look at the immediately invoked function expression at the bottom to begin with, we are retrieving a player from the DOM, and then we are setting its source object property to the return value of the fetch video function above. Now, if we have a look, we're starting to see we have some extra type information now. So foremost, we have a parameter for, a type for the URL parameter. So we're determining that any URL passed to that parameter must be of type string. And the second type annotation is for the return value of said function. So because we're using async await, and this is an abstraction over promises, we're specifying explicitly that it will return a promise that when resolved successfully will emit a blob instance. And within that, we're using the fetch API to call the URL parameter, and then we're converting it to a blob, which is also a promise. And then just one more place of interest. If you have a look at the invocation of query selector on the document.body node, you will see this type information we're passing between less than signs and greater than signs. And this is called a generic parameter. So by default, if we weren't to specify this, TypeScript would infer that method to return an instance of type element. But because we want to set the explicit source object property, we need to pass this generic parameter to ensure that the TypeScript compiler is aware that we're actually dealing with a HTML video element and not just any other plain element. Furthermore, you couldn't just pass any type to that. You couldn't say string in lieu of HTML video element because it also implements what's known as a generic constraint. And that means that any type that you pass in as that generic parameter, it must extend anything of type element. So it allows us to really make our development process a lot more robust. So why should we use it then? Well, just to reiterate, it ensures our code is type safe, and that reduces runtime errors. It enables us to catch errors earlier in the development flow, and one point I haven't mentioned thus far is it aids the refactoring of larger code bases, especially when breaking changes are required. So for example, if you imagine you have some sort of class that has various call sites across the code base, and it's a large project, and you want to make this surface maybe a bit more consumer friendly, then you can refactor the public methods and you can change that contract entirely, and by then recompiling it, you can determine that every other call site, every other place in which that code is consumed has been updated without finding out at runtime and having to trawl through all these errors as you're trying to run the application, which can be incredibly frustrating. Another benefit of static analysis is it provides us with excellent auto-completion features. So in particular, the TypeScript integration in VS Code is remarkable. And if I show you actually the example, so I've got this example in the browser. So what I can do is, if I try to request a property from player, so if I say player dot, we can see here we have all the type information for a typical element like add event listener, for example, add text track, append child, but then also, those two are generic to element, but then add text track, for example, that's a method of HTML media element from which HTML video element inherits. So we get all this amazing type information when we're trying to develop, and that can just speed things up. It's documentation within the editor. So back to the presentation. There we go, going that way. It can also be used to check regular JavaScript files, which means that little additional knowledge is required to get started, and this is what's known as gradual typing. So we don't have to specify any explicit types, meaning that either everything can be inferred, or it will resolve to an any type, which means the type can't be ascertained by TypeScript. And then gradually you can add that type information as it's required. So it means we can just gradually build up, we can just gradually build up a JavaScript file and build it up into TypeScript, as Morpheus said in that famous scene from The Matrix. So let's look at inheritance in TypeScript. So inheritance, just as a brief recap, is a paradigm in which an object or class is based upon another object or class. So in JavaScript, inheritance is prototypal. And this means that property access is resolved by querying the prototype chain until a match is found. So, for example, you have a dog object that has a prototype of animal, and animal could have the speak method within it, and then dog, when you call dog.speak, that resolves to animal.speak. So TypeScript supports the ECMAScript 2015 class syntax using class and extends that you may have seen already. So in JavaScript, this is just a syntactical sugar for that prototypal inheritance. But, let's go back. But in TypeScript, it follows the standard, but then it also provides compile time subtype polymorphic checking as well, which means that if we pass a subtype as a parameter that's expecting a certain type, then if that subtype is extending from a particular superclass, then it will be accepted as a parameter in that particular call site. So again, it's giving us more robustness and more type information earlier on in the dev flow. So here's a brief example of inheritance. So we have an employee class on the left where we're passing in a name as a string, and also it has a base role, which is just a string array, and it implements a toString method which computes a string representation of the employee. And then if we look at supervisor on the right, this extends the employee class, and once it's invoked the parent constructor using the super keyword and invoking that constructor, then we have the roles array to which we append a supervisor role. And we haven't had to re-implement toString, so we can see that we've been able to share that logic without arbitrarily introducing it again. And then if we were to run this and evaluate the output, we'd see Gareth would just be an employee, but Sarah would be an employee and a supervisor. And that hasn't required any duplication of this toString method. But what about inheritance in a larger app? Well, I spent some time on the internet and thought I could regurgitate some existing arguments, but then I thought, that would be a bit boring really. So I decided to write an application to tackle instead, which I call Pixel Weather. And what Pixel Weather is, essentially, is a front end for the Open Weather Map API. So it renders real-time weather data using a HTML5 canvas. And it's developed in TypeScript because, of course, that's the main focus of the talk. And I did it initially using inheritance before refactoring it to follow composition, so I could determine what the challenges are and how I could overcome them. So I'm actually going to pray to the demo gods, and I am going to hope that this will work. Is this font size big enough for you at the back, by the way? No? I'll make it bigger. Okay. So didn't realize I'd have such a high resolution. So if I go preferences, settings, but then I notice with that it expands the other parts of the editor as well. How about that bigger? How about 24? How about now? Perfect. Awesome. Thank you very much. Right. Okay. So, yeah, I'll change the terminal as well. Oh, 245. Whoa. Yeah, that is going to be one big font size. Thank you very much. Right. Okay. So, if I change into the correct directory, and make sure I'm on the correct branch, which I am. Now, if I run the project, so it requires an API key, so all I'm doing at the bottom is setting that as an environment variable, and then I'm running the DevScript, which compiles the service, the TypeScript server, and then it uses rollup to build and bundle the client-side code as well. So if I run this, so it's built. And then if I go to the browser, so I should be able to open a new window from here. Okay. Go to localhost. Here we go. Here's our app running, so I'm going to be brave and try to zoom it in as well. Okay, cool. So it's quite a straightforward application. So you have a search form for entering a particular city, but then this below it, this visual representation, this is HTML5 canvas, and we have some common behaviors across these visual entities. So the people and the clouds, for example, they're rendered using images, and then the elements of the road and the sky in the background, they're rendered as rectangles. And the clouds, they loop infinitely and they move. And that's relevant because of what I'm going to show you in a second. So if I show you how the app works, so if I pop in Riga, then we see it's 21 degrees and it's clear. So obviously it's the perfect day to be sat inside discussing code, right? However, if I put in this completely miscellaneous town I found in Kenya, then, oh, it's okay there today. And it was raining earlier, but it seems to have cleared up. So I'll tell you what, I'll show you on the video instead, because that's going to be quicker than finding a town, I think. So if we go back one. But I've at least been able to demonstrate to you that the app actually works and I'm not a massive phony, so I'll take that. Okay, so this is the town that was always raining. Then we have this rain that infinitely loops. So like the clouds, it infinitely loops across the screen, but then it does so vertically. Nonetheless, we can see there are many behaviours, or some behaviours rather, that are reused within the visual representation. So what are the downsides of my approach that used inheritance? Well, foremost, the coupling is incredibly tight. So both the person and cloud classes inherit from the same superclass, which I've called image renderable, which is responsible for rendering an image. And the clouds need to move and loop infinitely, but the people remain stationary, as we saw. And image renderable thus inherits from loopable, which in turn is a subclass of movable. But the person then acquires these behaviors, and yet we don't need them because the people remain still. So in terms of a code reuse paradigm, this doesn't make any sense. And furthermore, what if I wanted to introduce an entity that may be moved across the screen just once that was also an image, but then it didn't loop round again? Then this inheritance graph doesn't make any sense. So if we look at a code example, then we see that image renderable, it extends loopable, but now because person is extending from image renderable, it now acquires this behavior it doesn't need, and all of a sudden we have this inheritance graph that is a bit logical. And then also, within the cloud constructor, we're calling super, but because this inherits from what we determine to be a image renderable, which inherits from a loopable, which inherits from a movable, which inherits from a positionable, then we have to pass all of these parameters down to the super constructor, and then we have to pass further parameters down as we go up the inheritance chain, and it's just disgusting. It's a complete and utter mess. So, second downside of this type coupling is that it's incredibly difficult to test. So we have to call superclass methods using the super keyword to preserve any inherited behavior, as well as implementing our own. And this means that the next methods cannot be tested in isolation. Classes could be stubbed on input, but this is messy and error prone. So let's see an example of this. So this is a snippet of the image renderable that renders images to the context, and this extends loopable. But if we want objects to remain looping across the screen, then we have to call super.next, which breaks any kind of isolation. And generally speaking, it reinforces the tight coupling argument. It just has this really close-knitted relationship that is just really hard to separate. And I'd say foremost, it's just impossible to scale. So despite these cons, the pixel weather application I've shown you actually does function with inheritance, even if the graph is semantically broken. And that's because it's not the biggest application. But imagine if we had a code base all of a sudden where we had thousands of entities across it that shared various behaviors, and they shared like a different variety of behaviors. If they have no kind of relation, it makes no sense for them to inherit from one another. So this is the inheritance graph, and I actually had to do it I had to generate this horizontally because it's just that ridiculous. So everything inherits from this base class called an output object. And then you'll see, oh, okay, so the road inherits from an output object, right? That makes sense. The droplet generator, responsible for producing the rain. Fair enough. Positionable, movable, loopable, and then it's like, but why is an image renderable loopable and a rect renderable loopable, and why does a droplet implement directly rect? What was this guy smoking when he came up with this? Seriously, this is just completely ridiculous. So then, what is the alternative now that I've berated inheritance enough? Well, an alternative is composition. And composition is a means of building classes from other classes or functions to which common logic is delegated. And it's independent of inheritance entirely, which means that applications can trivially reuse logic as they grow in size and scale up. And TypeScript supports this primarily in two ways: via class or function delegation, just like JavaScript, but again, we have compile time subtype polymorphism checking. And then also it has an experimental feature called decorators, which are based upon an ECMAScript standard, but they're behind an experimental flag, so I went with the former approach. So this is how the code looks like using composition. So I'll show you the person class in the inheritance example, actually. That would be a good point of reference. So if I check out the inheritance branch, okay, and now if I go to person, so this is all person is, which doesn't look like a lot on the surface. It implements, it extends image renderable, but then we're passing all this information down for the positioning, the width and the height, the movement, setting it to 0 because it doesn't have any. Pretty messy, right? I know. So that extends image renderable. And then if we have a look at image renderable, that's empty for some reason. It's because I created a new file instead of opening the one I wanted to see. Go me. Right, anyway, this is image renderable, and it's a similar story, so that then extends loopable. So this is the code that reinforces the really strange inheritance graph I was showing you. And this receives like a context, a canvas rendering context, 2D instance, and this is responsible for drawing, but then we're calling super.next to honor the behavior of loopable. So let's compare this to the composed version. So this is the person in the composed approach. Instead, you'll see it's completely independent of inheritance. What we've been able to do here is create an instance of entity, which is just a generic container of components or behaviors. And into this, we pass an instance of this image renderable component, which holds the data and implementation for rendering an image onto a canvas rendering context 2D. And into that, we pass an instance of positionable, which isn't actually a delegate per se, because it doesn't have its own next implementation, but that's just a data container, effectively, that determines an entity's position. Now, if we look at the cloud, there we go. Okay, funny scroll direction. Yeah, if we look at the cloud in contrast to the inheritance example, it's a really similar story to the composed person, right? We create this new entity instance, we create an image renderable component, but then also we have a loopable component and a movable component. Now, the loopable component receives an instance of the movable because it can determine by its x and y speed the direction in which it's going. So we can also compose these components from other components as well. But nonetheless, we can see that we've totally broken free of this inheritance graph. And this is all statically analyzable as well, which means if I were to pass 120 as the width parameter for the positionable, as a string instead of a number, then we'd receive a type error. So we're able to break free from inheritance while gaining all the benefits of TypeScript and static typing. So what is an entity? Well, it's simply just a class that takes an array of delegate instances. So these delegates are the components such as positionable or image renderable. And all this does is when its next method is invoked in the game loop, which I can show you in a second, then it just invokes each delegate's respective next method. And what is a delegate? Well, it's merely an interface. So if you haven't encountered an interface, it's essentially, as opposed to an abstract class, which determines a semantic is a relationship. This is more of a has a relationship. It determines a capability, a contract that this particular class will fulfill. So let's look at an example of a delegate or a component. So this is the rect renderable. This is the logic for rendering the road and the background in particular. So all this does is it extracts the x position, y position, width and height information from the positionable instance, and then it fills the it sets the context fill style property with the desired fill, and then it merely fills the rectangle using the provided context. So this isn't relying on having to call super.next or any kind of type coupling, because the inheritance is no longer here within this architecture. So this is what we're left with. So I haven't included entity on here because entity is just a standalone class. We don't have a class for the cloud or for the person anymore. These are just generic containers of delegates. But if we have a look at the delegates that we do implement, like rect renderable, movable, loopable, or image renderable, they just implement delegate and nothing's inheriting from anything else, and all of a sudden that crazy inheritance graph has just been thrown in the bin and burnt where it belongs, really. So the benefits of composition, I hope some of them have stood out to you, but just to reiterate, the code base growth is uninhibited because there's no rigid inheritance graph. So, as I was saying, we can have like thousands of different unrelated entities now that share common behaviours, and we're not constrained to what inherits from what, and we don't have this strange superclass subclass relationship, so we just build things up really easily and organically. Individual components are better decoupled from their dependencies, so we're just injecting any dependencies in via their constructor, and this means we can just stub them really easily, and we're not having to find a way to stub supercalls, which is just a nightmare. And they can easily be unit tested because of that isolation, and delegates can be changed without necessarily breaking the implementation with other delegates. There might be a bit of dependency, but to add to that, the API surface isn't going to be affected when you change one particular delegate. And unnecessary logic is not directly invoked, because in the inheritance example, we had to call super.next. So for the person, even though it wasn't moving, we kept calling next, and that would invoke some logic. So unfortunately, I didn't have time to capture any benchmarks, but fundamentally, this could result in a performance improvement, and I do hope to capture this in Chrome DevTools one day. So how can we test components then? Well, because they're merely a class, a container of state, then all we have to do is typically we'd pass in some input by parameters, and we'd provide assertions on the output. Now, unfortunately, because I didn't want the Canvas part of the application to dip below 60 frames per second, I actually went for a mutable API. I mean, in an ideal world, it would have been immutable, and I would have been testing the return value. Instead, because we don't want the garbage collection to just generate loads of collections and sweep loads of stuff and compromise the performance of our app, then I took this approach instead. So what we're doing is we create a new instance of our rect renderable component, into which we pass a stub canvas rendering context 2D. We set a red fill, and we pass it the other dependency it needs, which is a positionable instance. And then we invoke next, which produces the side effect. And once we've done so, we can provide these assertions to determine that it's the correct fill style, and we've called the expected canvas instance methods, the context instance methods, as expected. So if I run that now, so this is just written with jest as well. So if I just run npm test, and it lints it as well. No, that is because I'm in the inheritance branch. So let me change to master, where it's all nice and composed. Okay, so if I try that again. So there's only one test in there, but it passes, and that gives us the basis to do more testing. Okay, so to summarize, inheritance can be appropriate for smaller applications or where we do have some kind of logical semantic inheritance graph and all the entities or classes have some kind of relationship. But an enforced hierarchy, generally speaking, makes it harder to reuse code as a solution grows. Composition, however, allows us to build classes from smaller delegates, and reuse can be achieved outside of an inflexible hierarchy. TypeScript then complements these larger composed apps with its type safety mechanisms, the static analysis, and components can, as we've just seen, be easily tested in isolation. It's possible to write integration tests for components and entities as well, but I don't have an example of that, unfortunately, but that's certainly possible. And that's it for my talk. Thank you very much for listening.
So it looks like we have time for a couple of questions. Michael's asked, what tools do you use for testing TypeScript, particularly for testing server-side Node applications written in TypeScript?
Well, I'll show you now. I'm going to mirror my display, though, so I can actually see my editor on here. So if you bear with me 1 second, hopefully this won't look completely terrible. Okay, cool. Now I can see my own editor on my own screen. Okay, so I'm using Jest. Now, I've worked in some setups where I actually compile the TypeScript first, and then I run the test suite against the transpiled code. But there's always a compromise I've found where you can test the transpiled code and you're potentially catching issues with that code earlier on. But then in the development flow, you're also really just wanting to test the behaviors of your own units. So if I open the Jest config, then what I'm doing is instead of transpiling using the TSC compiler, I'm using the TS-Jest transform, which will compile the source code on the fly as each test is invoked. And then I point to a server config file. And this is just because I have 2 config files. One of them, what it does is it transpiles the TypeScript to common JS modules, which are required for Node because ES modules aren't supported unless one uses a flag. However, for the client, I'm transpiling to ES 2015, and that is because I'm using Rollup as my module builder, which not only supports ES modules, but then also it performs tree shaking on that code, and I'm working on a project at the moment where I've witnessed it remove unused code, and that's really successful in reducing the bundles. But back to your original question, I'm not particularly doing anything special with the server testing because I'm just testing the client code, but because I'm using Jest, which runs in Node, I'm using this particular server-side config, which is also shared with the actual server, which I can show you. So this is the Express server, and doesn't really have any explicit type definitions, but we're able to infer the types really well. So, for example, if I hover over the get method of our Express app, you can see it has the type information associated with it. Request has type information available because I installed the type definition from definitely typed. But to go back to your question, I'm not doing anything special, but it's just Jest that performs essentially on-demand transpilation via TypeScript Jest.
So we are up for the time, so thank you, James.
Cool, thank you.